Well, good afternoon or good morning, everybody. The goal of today's presentation is just to give you an idea of what kinds of information needs to be gathered to identify either an RTD or a thermocouple. We're going to kind of focus just on those two technologies. They're kind of the most common ones that you're going to find out there. There are others which could be confused with it, like a thermistor would have like a two-wire connection, but I'm really not going to get into that too much. So we'll just focus on the RTD and thermocouple versions, and then also some of the accessories that go with them. So it's one of the most popular webinars that we've done is this, how to identify these types of devices. Some of the terminology that gets thrown around is, and I just go down the list here, some of the more common ones are RTD, which is a resistance temperature detector. That's kind of the all-encompassing definition of this type of a temperature sensor. A PRT is a type of RTD, so it uses platinum wire. There are others that use nickel or copper, but most common is the platinum resistance thermometer. R0, it's just the resistance as measured at 0 degrees C. And then the temperature coefficient of resistance. Now, this is really important to identify which temperature coefficient the sensor has that you're trying to replace, or if it's a new system, just to make sure that you get the correct temperature coefficient, because it's really important to match that to your electronics that you're connecting it to ensure that you get an accurate measurement. And what it is, a real kind of simple definition is that it's the amount of resistance change per degree of temperature change. I'm going to talk about this just a little bit more later on, and we'll go through a little example. The R0 and the temperature coefficient are defined by a couple of standards. There's an international standard and then an ASTM standard. And finally here, there are single and dual and sometimes even triple elements. And so what that means is it's, rather than having just one sensor inside the probe housing, there could be two completely separate ones. Typically that's done so that you can run one of those over to a controller. Another one may go to a chart recorder or a local indicator. So those are just some of the common terms that get thrown around, and it's helpful to know those. First off, one of the first things to look at here would be the number and color of lead wires. Each manufacturer will have color codes. We typically use red and white and black and green, and a typical dual element like shown here, this is going to have 6 leads, and so one of those sensing elements would be the red and white leads, and the other one would be the black and the green. Here is just an example of a 3-wire single element. If it were a 4-wire system, it would have another white wire here, so it would be 2 whites and 2 reds. Now, the international standards and the ASTM define the colors a little bit differently. So you're going to see in the case of a dual element, you're going to see a yellow lead instead of the green. And there are several manufacturers that are still using the older color codes. So in place of these yellows, they're just going to be green, and it helps to know it's just kind of a legacy thing. So it's been around for 50 plus years, and they just haven't changed. So after looking at lead wire colors and numbers, one of the things that you can do is to check the probe in an ice bath. This requires an ohm meter and some crushed ice in some kind of an insulated container. And testing it, you should end up if it's a Class A probe, which is the tighter tolerance, it's a tighter manufacturing tolerance, plus or minus 0.06 ohms, and the Class B is 0.12 ohms. That's a real quick way to do that. If you don't have an ice bath, you can just check the probe. If it's at roughly room temperature, 72 degrees Fahrenheit or about 21, 22 degrees C, it should read about 109 ohms. And you can measure that between the white lead and one of the reds. And to get a more accurate measurement, you can manually eliminate the lead resistance. So if you were to go in and measure the resistance between these two red leads, and what that does is it approximates the lead resistance between the red lead and the white lead, which includes the platinum sensor here. So you would just subtract what you measured with the two reds from what you read between the white and the red lead, and that way you're left with just the little platinum sensor resistor resistance. And that should be about 109 at room temperature. If you have a hot block that you can put it in, it should read about 138.5 ohms. And that's if it has that 0.00385 temperature coefficient, which is the most common one that's out there. One thing I wanted to mention here is with these sensors, by definition, this temperature coefficient is 0.00385. So what that means is that there's 0.385 ohms of resistance per degree C of temperature change between 0 and 100 degrees C. Now it varies a little bit as you move between 0 and 100 because it's not a perfectly linear relationship. But on average, it's about 0.385 ohms per degree C. So that can help you out if you're trying to just estimate a temperature in between 0 and 100 if you're just trying to do a quick field check. Thermocouples, and I guess, Jeff, if there are any questions, feel free to interrupt in between sections here. I don't think I mentioned that earlier, but yeah, just jump in if there are any.
Yep. Thanks, Bill. That's a good reminder. If you do have questions, just go ahead and type them into the chat or the Q&A. We'll try to catch them as we're kind of going along. Because if you've got a question, I'm sure some other people have questions as well. So don't be shy, and we'll try to get an answer for you.
Okay. So thermocouple lead wires, they're typically just going to be 2 leads per sensor. And these are color coded for the kind of the base type thermocouple. So that's a type J, K, T, or E. And on the diagrams here, some of these it's real obvious that it's blue and red. So that's going to be a type T. The red lead is always the negative lead. Type K, yellow and red. And some of these are going to have like a brown insulated cable on them, and one of the leads will have just a little stripe on it that is really hard to see sometimes, and you can just barely see it here. This is a purple stripe on it, which indicates that it's a type E thermocouple. And on the high temp versions, these are all like platinum and platinum rhodium conductors on them. Will either be a type RS or a type B. And what this manufacturer did, they actually wrote R right on it and labeled the positive lead right here. With these, there's really no other way to do that. They typically don't color code the leads. So it'll have to have some kind of an identification listed on it. And this is probably their part number or something here. So they if there is no identification, then it's just going to be really tough to know which of those 3 versions that you may have. Now the standards do, they define these color codes. Unfortunately, they're a little bit different between the ANSI standards, and then there's an IEC standard. So with the most common ones here in the U.S. with a white and a red lead, it's going to be a type J. If they're not color coded, you can use a magnet, and one of these leads is iron. So the positive lead is iron, and it's very magnetic, of course. So that's one quick way to do. The type K, one of the leads is very slightly magnetic. Type T, one of the leads is copper, so you can kind of tell just by the color sometimes. And type E, they're completely non-magnetic. And then the type N thermocouple, which is very similar to a type K, they'll use orange and red. Now, of course, the IEC standards are all different, so really kind of depends on, on what, where you are purchasing the thermocouples. So you're going to run into different color coding depending if it's someone that's building to the international standards versus the old ANSI standard. One other thing to look at on thermocouples is whether it's a grounded junction or an ungrounded junction. And what this means is that the two thermocouple wires, when they're welded into the very tip of the sensor, that is a grounded junction. So you'll have continuity between the lead wires and the probe sheath. And if it's an ungrounded junction, this little thermocouple hot junction here is completely electrically isolated from the probe sheath. So if you were to test that with an ohm meter, you would not get any continuity between the lead wires and the case of the probe. So that's real important to know when you're trying to identify a thermocouple for replacement. So the physical characteristics of the probes, like for example, the ones that install into a Thermowell, they're going to have some kind of a spring loading mechanism on them. And that needs to be identified. One of the more common ones would be a threaded fitting where the spring is internal inside this housing. There are others where it's exposed, where you can see it, such as this little bayonet lock here. This type is typically used in, like plastic injection molding equipment or other types of machinery where there might be just an access hole drilled into it, and these will just go into that bore and then hook on with this little kind of a little quarter turn twist lock connection. And then there's I guess we could call this a DIN style, or kind of a European style, where the terminal block is attached to the probe and the screw terminals here provide the spring loading into the Thermowell. And I'm sure there are other types out there. In fact, I know there are, but these are some of the more common ones. Now, a lot of manufacturers are going to put a serial number on the probe, and this is important for traceability, which is why they do it. It also helps them identify the probe when it comes time for replacement. Sometimes they're a little hard to see. This one was electro-etched on here, and it's kind of gotten rubbed off a little bit. They may have been put on with a little vibratory pen, so they might be just kind of scratched in, and those are really hard to see. There may be a bunch of other numbers on the probe. This happens to be a heat number right here for the materials of construction that were used. So that's these two numbers. And then they had a SN, which I guess we can assume means serial number, and then a little 6-digit number on here. Again, this one's down on the probe sheath. So typically the manufacturers will have tested the probe's resistance just to make sure that it meets the Class A or Class B standards. And the serial number helps track that back to an international standard so that you know that there's this continuous path of traceability. So, Thermowells. I don't know, are there any questions on the RTD and thermocouple characteristics, Jeff? I'm not paying attention to the chat box here.
Yeah, it doesn't look like we've got any questions right now, Bill, but
okay.
One thing I just wanted to mention is as you kind of go through these, it is always kind of a process of elimination. So as much information as you can give the manufacturer when you're trying to identify these things, the closer or the easier it is to be able to identify the right thing. I know a lot of you, one of the other things, and Bill, I don't think you've got it in your presentation, but we run into is RTDs and thermocouples. The part numbers tend to be really, really long. You know, in general, you know, sometimes it can be short, but usually they end up being fairly long because they describe what the sensor is. So a lot of times we'll run into where you've got something in your system, but because you ran short of characters in your ERP system, or you know it get entered inaccurately, you know a 0 instead of an O, something like that. It can be difficult to sometimes just identify them right from the part number that you have in your system. But if you share the part number you have in your system along with you know the specifics of the number of wires, the number of colors, and even as much as just measuring out, here's the length of the probe. This is what I've got. Those are the types of things that can help us identify and get you the right item.
Yeah, that's a good point. That, along with the serial number, that can help fill in a lot of those missing characters. So, okay, Thermowells. These get just a little bit more complicated. One of the more common issues we come up with is like, well, what length probe do I need for this Thermowell? If we have the bore depth of the Thermowell, that's really the most useful dimension to supply. With that, we can calculate whatever extra length might be needed for the distance between the well and maybe a connection head or whatever a transmitter head that may be attached. So that's the most important one. An easy way to measure that is take a piece of wire or an old probe or whatever, shove it in the well, mark the length, and then measure it. Some of the other dimensions that may need to be supplied would be the lag extension, which is this T dimension. And these little variable letters, these are fairly commonly used with Thermowell and temperature probe manufacturers. So the U will be the immersion length. The T is this lag extension, which is just some extra hex on the, in this case, on a threaded Thermowell. So if you have insulation on the pipe, you may want to have that hex extended outside of that. So that's where that number comes in. And again, bore depth down here, most important one to know. There's lots of different process connections on Thermowells, and I'm just going to run through some of the more common types here. So we've got the threaded and then the ANSI pipe flange style. And we're showing these. This is a stepped or reduced tip stem on it. And this would be a tapered stem. Example of a weld-in Thermowell that's typically used on sanitary tank applications. And a socket weld version, and this would be typically going into a little ASA weld socket on a pipeline with it showed with a tapered stem. Some of the other kind of a little more specialized Thermowells, we have this in-gold style, which is typically used in a bioreactor tank, and it slides into Oh, just a little sleeve that's welded on the side of the tank, and it's sealed up with this little O-ring out here. And then this threaded nut holds it onto the adapter on the tank. Van Stone, this is the flange that's actually, it's captured in between what they call a backing flange. And this one shows a tapered stem. And finally, for sanitary applications, there's a hygienic ferrule, sometimes called a tri-clamp fitting, which is an old trade name. This one's shown with a straight stem. And here is another sanitary Thermowell that has a hygienic ferrule for the process connection and also the instrument connection. One of the other things for sanitary Thermowells would be to know a good estimation of what the surface finish is. And typically just by looking at them, you know, like this one probably has about a 20 micro-inch average surface finish. You know, it looks a little dull. There are no visible scratches. If you rub your fingernail on it, you're really not going to be able to have it catch on any scratches or anything. If we go back on a well like this, where it looks like kind of a mirror finish and you can see yourself in it, this one's probably down around 10 micro-inch finish. So that's just a quick way to kind of estimate surface finish if you're trying to replace an existing well with a new one. Another style of sanitary well that's fairly specialized is what we call an elbow style. These will typically be used for very small diameter lines, like maybe 1/2 inch up to about 3-inch diameter. And they work really well for doing that because the probe can be installed in the run of the pipe here, so you can get sufficient immersion length to get a good accurate measurement. Now these will have either a weld end like this that'll be installed with an orbital welder. There are also the hygienic ferrules can be attached here and have it removable if it's necessary to be able to do that for cleaning or replacement. Heat numbers you will find on the Thermowell, and these are important for identifying the chemistry of the material that was used for the part. Now these will typically have a prefix of HT on them most of the time. Sometimes it's just going to be a bunch of numbers and letters, and they can be confused for a serial number. Typically Thermowells will not have a serial number on them. This one over here, that they stamped the material, the 304 stainless, and then this heat number. And the heat numbers are going to be listed on the material certificate also, so you can match them up that way. And given no information or heat numbers about the well, we can use a device that uses X-ray fluorescence to identify what the material is. It's not going to give the exact chemistry of the material, but it will tell us whether it's like 316 stainless or maybe one of the more exotic alloys like Hastelloy or you know, Al6XN, for example. So that's another way to do that. Typically just called positive material identification, or PMI. And connection heads, these were used to terminate the temperature probe and provide some protection for it. A lot of different materials here, a lot of different sizes. Typically they're going to be plastic, aluminum, cast iron, or stainless steel. Things to look at here would be the size of the threaded ports on them. Right here, you can see some of the other ports. Typically, the conduit side is going to be 3/4 inch NPT. Some of the really small heads are going to have, some of them have actually a straight thread, so it's not really an NPT or a tapered thread. It's just going to be a straight thread. So we would need to know what those characteristics are to be able to match up or to supply a replacement. And some are going to have hazardous atmosphere ratings on them. We have a couple examples here. This would be a Class 1, Division 1, Group A, B, C, D. So that just means that it could be used in a like acetylene atmosphere, which is the most explosive. This one's got, let's see, this would be FM, Canada, and US. So if you're not sure what all this means, you know, send a photo. Can help identify it. They can be used to house a transmitter. This is just a little 2-wire temperature transmitter here. Temperature indicator. Some may just have a terminal block in them. Typically, they'll be ceramic, and the terminals here, the better versions, they'll be nickel-plated brass so that they don't corrode. So with that, just to kind of wrap things up here, and we kind of went through it pretty quick, but when looking at an RTD or thermocouple, identify the lead wires, the number of wires, and the color. We talked about some electrical tests, just a resistance check in an ice bath or at room temperature. We have typically about 109 ohms at room temperature for an RTD. We're looking at a Thermowell, or even a probe that may be immersed directly into the process. We need to know the connection size and type, whether it's threaded, flanged, some type of sanitary connection. And probes that go into a Thermowell, the spring loading style. Look at the connection head. Some of these are also have an epoxy paint on them, which is typically white and used for pharmaceutical or food beverage applications. And then what's inside the head? Is there a transmitter? Is there a terminal block? Do you have an indicator? And sometimes, a picture's worth 1,000 words. Take several photos of the complete sensor, lay a tape measure beside it to get some good estimations of the lengths. Pictures inside the head, outside, several different angles. And typically with that, the probe can be identified very closely to what it actually is. So anyway, with that, I think we are all wrapped up here. And if there are any questions, we can go through some of those right now.
Yeah, if you do have any questions, do go ahead and type them into the chat or the Q&A, and we'll try to get you an answer. Did also want to mention that it will be coming up here within the next month. Excuse me, next couple of weeks. We'll get a new RTDology schedule out. What our next few sessions will be over the coming months. So look for that announcement. Did also want to mention one other thing that sometimes comes up with a RTD versus thermocouple, trying to determine which is which. If you've got a sensor that only has 2 wires, typically it's going to be a thermocouple, but it could be an RTD. Not as common to have 2-wire RTDs, but they are out there. One of the kind of key differentiators can just be the temperature range that you're trying to measure. If you're above 500 C or 900 F, it's going to be a thermocouple. There are some RTDs that can operate at those temperatures, but they're fairly uncommon. So really, if you're measuring the higher temperatures, it's probably going to be a thermocouple as opposed to an RTD. So that's just something that I wanted to mention. Looks like we've got a couple questions here, so let me But through them. There's actually just a comment about surface finish, and sometimes regardless of the RA of the surface finish, if it's electropolished, you'll get a shiny surface finish, but or that mirrored finish. In the sanitary world, typically it goes with a more finely polished as well when they do the electropolish, but that certainly will tell you if you get that mirror finish, you may have some electropolish on there as well. Here's a question about going back to connection heads. Do you see those more in any particular applications, or are there common points in a process that the connection heads are necessary?
I always like to use a connection head just because it makes maintaining the probe a lot easier than having a big long cable attached directly to the probe. It also helps protect the back end of the probe from moisture or wash down. And I'm also kind of reading ahead here. We have a question about connection heads and cleaning chemicals. Some of those chemicals, if you were to just use those on a regular exposed probe where the cable or lead wires are coming right out of it, that can actually wreck the probe over time because that liquid stuff is going to get inside and cause some shunting between the leads in a lower than actual temperature measurement. Especially for like food, beverage, and a lot of pharmaceutical applications, a polypropylene head works really well. Aluminum, usually not because of the caustic chemicals that are sometimes used. They just tend to corrode them. Even if you have like an epoxy paint over it, that can get chipped or damaged, or the stuff seems to find its way through it somewhere and cause a problem. So yeah, as far as other industries where connection heads are used, I think especially like petrochemical, they typically always have connection heads on their devices. It may be housing a transmitter. A lot of times a local indicator will be also on there. About the only times where you need to get away from a connection head type is if there's some kind of real estate problem where there's just no room for it. So there are smaller heads, but sometimes it's just not possible to get in there to hook up conduit and everything else. So then
I think
you really have no choice.
What we have seen over the years is there is a move. I'm not going to say necessarily away from connection heads because they're still very, very popular, but there is a growing number of direct connect. So essentially, you have something like an M12 connector. So you've got cable running from your control and to a M12 connector, and then a M12 fitting right on the backside of the sensor, and you're plugging those two in. The benefits of that is, one, it's size. It's a smaller footprint. Another benefit is it can't be hooked up incorrectly. The connectors only go on one way. So, and it's easy to remove it and reinstall it if you're going to either replace the sensor or calibrate the sensor. So we do see, more and more, especially in I guess we see it mostly in biotech, where they're on some type of a skid and there's just not a lot of room for to have the larger head. It is another connection point, but Bill, any comments on that?
Well, yeah, one thing on the M12 and other style connectors, a lot of those will have an IP rating of about, I think it's 67 when they're mated. So they do provide some protection for the inside of the probe. If you have a short extension cable coming from the probe and then the connector, then you've still opened yourself up to potential problems if it sees wash down. But those that have the connector attached directly to the probe, they'll typically have an IP67 rating, which means you can, splash water or spray water on it, and it's going to be fine.
Okay. Another quick question. What is the reason for the dual element thermocouples in the same sheath? Or I suppose the same could be said for RTD as well, dual RTD.
Yeah, you typically will need separate thermocouples if you're going to use, use the same measurement point for a local indicator and a controller, for example. And there are people that will build the thermocouples. They'll actually, if it's like an ungrounded junction, they'll actually isolate the two thermocouples from each other. And so you're completely electrically isolated from the probe sheath and between each of the thermocouples. And that's probably the best way to do it. Would seem to be fewer troubles with any kind of electrical noise or interference. In the case of a grounded junction, they're just all twisted together and welded into the tip of the probe. So
typically the reason for it, it could either be that they want two different signals, one going back to the control, another going to maybe a local display, or maybe it's going to a chart recorder, or it's in some cases it's used for redundancy, so that they have just one of the elements hooked up, or one of the thermocouples hooked up, and if there's a failure at some point, then they have the other one that could be used as a redundant, at least in the short term, until they get the sensor replaced. That's the way some people do it. It can be a little risky for the redundancy thing, because both elements have seen the same environmental conditions over their lifetime. So if one has failed, it may not be too long before that second one goes as well. But it does give you kind of a short-term way to assess it. Some people will also use the second element as to do their calibration, or to do a check on it while it's in process, in place, rather than having to disconnect the other element. So those are some of the reasons that people use them. I think another question we've got here, Bill, is does the RTD or thermocouple have to be assembled to the explosion-proof head to meet NEMA requirements, or can it be attached in the field?
Typically, a temperature assembly will be fully, well, it could actually be done either way. It kind of depends on what approvals the manufacturer has on their explosion-proof assemblies. Some of these the requirement is that there's an explosion-proof housing on the probe, and Thermowell assembly, or even if it's a direct immersion style, because there's a test they need to do to that assembly before they ship it out, or before they hang their little FM tag on it or explosion-proof tag on it and ship it out. Others are approved for any explosion-proof enclosure, junction box, connection head, transmitter head, indicator, whatever, and that can be assembled in the field to the sub-assembly, which might be the temperature probe and a Thermowell. So it can go either direction.
Yeah, I think typically the NEMA requirements, that's on the head itself. So if that was assembled in the field and everything was assembled correctly, it would meet the any water, dust, ingress requirements that it has. The FM, or the explosion proof, is different than NEMA, and that's where it's really dependent upon what has been tested and classified and exactly what the approval is as to how that needs to be assembled, whether it needs to be assembled ahead of time or can be assembled in the field. Just a comment, which I think is a good one from Jody. This kind of goes back to the dual. You know, some transmitters do have the capability to have two inputs. You know, so one will be kind of will be the default as the output signal until the other one goes out, and then it can switch over automatically. So there are some transmitters that have that capability to have those two inputs, either for redundancy, safety, and/or sending the signal to two different places. So good. All right. Well, it looks like that's it for the questions, but I do want to remind people, if they have questions in the future, just on whether it's something we went over today or something else regarding temperature measurement, feel free to go ahead and give us a call or send us an email, and we'll work to get you an answer to your question, and so that you can get your measurement point. With that, do go ahead and join us on our different social media. We do have a LinkedIn. There's a couple LinkedIn groups, also on Twitter and Facebook, so do go ahead and join us there, as we do make general posts on a regular basis. So with that, thank you very much. Take a look for what's coming up here in a couple weeks. We'll send out a new schedule to see what we've got for RTDology, and we'd love to have you join us at those sessions. So have a great day, and we'll see you next time.